Hello everyone, today I'll be presenting Score Jacobian chaining, the maths behind Score Jacobian chaining, and some of the modifications that I've done to change score distillation sampling inside RealFusion with Score Jacobian chaining. So let's start. I will start with saying that, Score Jacobian chaining is a similar approach to RealFusion because they're both score-based models. RealFusion uses score distillation sampling, and Score Jacobian chaining uses Score Jacobian chaining. So they're both score-based models, and they are a subdomain of diffusion models. In this work, in order to generate a 3D asset, they learn a 3D score. And, Q here is a probability distribution. And, the author says that, let's look at the gradient of the log of Q. And the whole 3D score is the sum or average of the score of its rendering in 2D space. They multiply this with a render Jacobian here, which is another gradient. This way, they weigh the renderings. So I should now move on to the paper. I will start with the first equation. So we have let's say I have a sample in hand named Y. I'm adding a little bit of noise. To my sample Y. Later, I have a pre-trained diffusion model, and this diffusion model is actually denoiser, denoted as D here. Later, by passing this into my denoiser, I'm trying to denoise it. And I'm writing the loss according to the difference between the original image, which is Y, and the denoised image, which is dy plus the noise. This way, I'm trying to sample Y. Now, this differs from classical diffusion models because, some diffusion models do not directly model the denoiser. Most diffusion models try to predict the noise on an image. So here, x minus variance multiplied by the noise here is like means that this is a non-classical way of modeling. This is a non-classical diffusion model where I'm trying to directly understand the input instead of not the input but the 2D image instead of predicting the noise. So here we have the definition of score in the third equation. So denoiser minus the original divided by the square of the variance of the noise that I'm adding is the estimation that is being made in here. So again, denoised minus the original divided by the square of the variance of the noise that I'm adding is allows me to calculate the score here. So let's move on to equation 6. I will pass these because they're mostly similar to one another, and they are not as important as the following equations. So on equation 6, I've talked about 3D score before, and 3D score is proportional with the average of 2D scores. When it's a random variable, it's referred to as expectation. So this actually is the expectation. So here, this was actually the expectation. At first, I called it, the sum or the average, but because these are random variables, it's called an expectation. So let's move on to equation 10. The second part is the render Jacobian, and render Jacobian is calculated according to the angle that I look at the 3D shape from. So it's most likely some camera parameters like distance, angle, and such. For the 2D score, we use a 2D pre-trained diffusion, diffusion model and calculate the 2D score. So I sort of try to explain what's happening during the calculation of the Score Jacobian chaining. So now I will explain it geometrically. So what is actually happening behind all of these calculations? So let's say that we have a point. Okay, a point is a rendering of the 3D shape, which is two-dimensional. Okay, so I added a little bit of noise so that this XPy is a 2D image. So I add a little bit of noise to it, and I denoise it using my denoiser, and I basically follow this green line to add a little bit of noise, and blue line to denoise it. So I end up here. And doing this once causes the problem of out of distribution. So they're having an out of distribution problem, and while following these two steps. So in order to solve this, they use perturb and average scoring algorithm. Simply, this perturb and average scoring function does the adding of noise and denoising step, multiple times within this, within this area. So I add a bunch of like it's, instead of taking a single point as reference, it takes multiple points as reference, and it adds different noises every time. So instead of computing the blue lines, and it computes the dashed brown lines. Okay, so perturb and average scoring calculates, these vectors, which are, indicated as, dashed brown. It takes the average of these brown vectors, and this way it's able to solve this out of distribution problem. So I think I should scroll back up to the equation 11, where I can now easily confidently say that we need to maximize the 3D score according to theta, and theta is the output, a parameter that we feed into a nerve. Right? So that's basically it. So it should now make geometric sense, from a geometric point of view, this is what's happening throughout this optimization phase. Now I will dive into what each equation does, so that I can tell you about the maths behind this optimization process. So as I've said, we know we want to maximize the log probability of theta. We say that we are going to take the expectation. What is our theta? It is our 3D representation with same parameters. This rendering with some representation, with some parameters, produces a bunch of 2D images. And we're going to say that our gradient is the expectation over all of these images. So line 9 makes sense. It says that we're going to average over views. All right, so line number 10 again. So we are going to do chain rule here. Line number 10 is where we do the chain rule. We're going to say that the grad log prob of theta is called the score. So the score is called grad log prob. There's the expectation in different views of the grad log probs of the 2D image times the gradient of the probability of the image of the data with respect to underlying parameters. So this is the chain rule, okay? What's this saying is that, let's say that you have some generative model and you have a setup which goes from nerf representation. You do some rendering, you measure the probability of the render. This is saying that if you could backprop through that, then all you do is that you backprop through the first part, okay? Backprop through the first part, and then you backprop through the second part. This is just the Jacobian of the first part and the Jacobian of the second part, actually. But, the Jacobian of the whole thing, we can also refer to it as the Jacobian of the whole thing, because Jacobians are small and linear, and everything is, a derivative. Again, moving on to equation 11, it's just reframing the same thing. It's just giving the things that 10 named. And the first part is the first part is a 2D score gradient of the log probability of this image in image space, in 2D space. And then the next part is the gradient of the image with respect to the underlying parameters, which produce the image, okay? So that, we can say that's the Jacobian of the differentiable rendering process, So, a 3D score, which is what I'm trying to optimize, is the product of these three things. And so the second thing of these three things is the render Jacobian. Just by backpropping through, we just backprop through it using, PyTorch, and we shoot some rays, aggregate over the rays, and it's all X mols and additions. So they're all differentiable. The first part is the whole thing, including gradient. The whole thing is the diffusion model. This is what the diffusion model predicts. The diffusion model is a function from X, which is some X of pi. Pi is some camera parameter. The diffusion model is a function from X to some approximation of grad log pi of X. So we predict the noise. We actually predict grad log pi of X. So this is something that's really, really similar to RealFusion, actually. And, from a PyTorch point of view, we really have to understand, autograd and such. I will now move on to how I implemented Score Jacobian chaining and how I replaced score distillation sampling, and how I combined the two. So here is like inside the SD file. Inside the SD folder, I've added this combined SJC SD file, and inside I basically changed the train step function. So I will first present the combined version. So in this modified version, I added the gradient computation from second code right after the original gradient computation in the first code. The new gradient, grad2, let's go to grad2, okay? So the grad2 is computed using the denoised image, DS, and the noisy image, ZS. Then the original gradient, grad, and new gradient, grad2, are combined to form grad combined, which is used in the backward prop. So that's mostly it. After the original gradient computation, a variable called chosen OS is defined as a tensor of ones. This is equivalent to chosen variance S from the second code, where it is chosen randomly. Like I basically wrote this text where I compare the previous version of this to the current version, and that's what I'm currently reading through right now. Following this, a noisy version of latent model input variable is created, similar to the creation of ZS in the second code. Here, noise is added to the latent model input, scaled by chosen variance S. Then a denoised version of this noisy image, ZS, is created using ViewNet model. Should be here, okay? The equivalent of model denoise is in the second code, is in the first version of the code. is stored in a variable called DS. Okay, now the gradient from the second code named grad2, okay, are added together to form the combined gradient, grad combined. Instead of calling the backward method with the original gradient grad, it's now called with the combined gradient grad combined. Finally, pseudo loss is calculated based on the absolute mean of the grad combined. So that's basically it. If you would like to see some outputs, you can go to my YouTube channel and see some of the outputs of the versions that I've created here. I have positive Score Jacobian chaining, negative Score Jacobian chaining, and a combination of Score Jacobian chaining and score distillation sampling. So yeah, that's basically it. Thanks a lot for listening to me.